changing matrix rank. So I will start with some very basic definitions. So let's say that we are given a matrix M, which is an n by n matrix over a field F. So the rank we define, there are possible definitions. The size of the largest submatrix with a non-zero determinant, and the number of linearly independent rows or columns of the matrix, and the smallest R such that M can be written as A times B, when A is an n by R matrix and F is an R by n matrix. In fact, one can argue that using basic linear algebra that these definitions are equivalent if we are working over a field. In fact, it is true if you are working over an integral domain. We don't need field, but yeah. So we have, in fact, there is one more interesting definition that the smallest R says that n can be split up into, let me write that, the smallest R says that m is equal to where each AI is of rank 1, and I'll have a definition for rank 1 as the multiple of rows or columns. So every row is expressible using a single. So then we can add this definition also to that. So one can prove that all these are equivalent if you are working over integral domain. Now let's ask the question: what is the, so if I am given a matrix M and a value R, what is the complexity of testing? Is the rank of M is less than R? Okay. So we call it as rank bound. The notation will be rank bound, and it's easy to see that using Gaussian elimination this can be done in polynomial time. And it was an open problem for a long time whether it can be parallelized. For example, if you look at Gaussian elimination algorithm, it's inherently sequential, like step after step. So can one parallelize it? And the question was answered by Mulmule in 87 and Chisto in 86. Both were independent works and two different methods. They say that this question can be answered in parallel. I mean, in the sense that the rank bound problem is in NC.
And what about Xan?
Sorry?
What about Xanki? He was earlier, certainly. Because rank computation is the same as solving linear equations. And Xanki was certainly earlier than Mulmule and Chisto also. In 1985, I think.
Oh, then okay. I'm not aware of that work, so maybe I'll start.
C-S-K-N-K-Y.
Okay.
He proved that linear equations is in C, and that is precisely what you are stating now. Why? Mulmule is correct, Chisto was also great, but Xanki was.
Yeah, so I am not aware of that fact. I'm sorry. So okay, so I'll check it out. Thanks for the point. Okay, so let me continue. So we are not really going to talk about rank bound. So of course this has very motivation from different linear algebra, control theory, algorithmics, and even complexity theory. So in particular, complexity theory is interesting because we want this to characterize various complexity classes. It might facilitate the well-developed algebraic techniques to solve this problem. I mean, solve this problem in complexity theory. Okay. So let me get to the problem that I will be talking about today. It's about a natural optimization question that arises in the context. So we ask how close is the M to a rank R matrix. Okay? So N is the rank R matrix that we are talking about. So how close is it? Now there are many questions. How does one define closeness? And okay, so we have various options, like we can define the norm of M minus N, where entry-wise difference, and the Hamming weight of M minus N means the number of places where M and N differ. And the next question will be the representation of the closed matrix. If you are working over an infinite field, I mean, so what is the representation that we are looking for the nearest rank R matrix? Especially if you are working over reals, for example, I mean the nearest matrix may not be representable in the form, okay, in a bounded form. The interesting part here will be we are interested in bounds on all these parameters that we are looking at, the norm, having weight. And in fact, if we don't have bounds and we are interested in complexity of computing them, in fact, even further, if we are interested in approximating them, so there are several questions that are in the contrast. And in fact, this also has many practical applications. So let me connect this to some of the previous talks in this workshop. So one is, okay, it didn't explicitly appear, but there is this literature about low-dimensional representation of large volumes of data. So what we are looking at is we have many objects and there are many parameters for the object. For example, color, thickness. I mean, different, which could be very different. And we can think of a matrix where so there are these properties listed and objects listed. And typically in the practical application, this matrix will be very large. So there will be a 1 if the object I satisfies the property J. And this matrix, I mean, we would like to represent it in as minimum storage as possible. I mean, we want to say that okay, there are only few of the objects which influences the other, or there are only few of the properties which influences the other. So basically, we are looking at a concise representation of this matrix. So that kind of, I mean, if you have to take a linear algebraic view to that.
But this is real matrix or Boolean matrix?
Oh, it's a 1, 0, 1 matrix. Yes.
And rank is computed?
Rank is computed. So
modulo 2 or what?
Modulo 2. I mean, I'm just saying an example. I'm not being precise, but yeah. So it's kind of appearing roughly in that application. So the another thing is the Netflix problem. This is a DVD rental company in the US. What they do is they have this table with users and movies. So users rank the movies if they, according to them. For example, they have a rank 5 for this movie out of say 10, and this 7. So this is user I, and user J has another ranking. And the conjecture or the vague idea is that if I is a friend of J, he will say that okay, these movies are good, so the ranking of J will kind of influence the ranking of I. And so this table is actually of low rank, I mean implicitly. So then low rank approximation of this is also good for the rental company to handle this data. And also that there are some users who haven't seen some movie, and the rental company can suggest you this movie is good according to your matrix, and you can go and see. So their suggestion is also an interesting application. But so basically that you can represent all these in a low rank. I mean, it's believed that it's a low rank matrix. Okay. Now this also arises in the control system. Maybe I'll skip that. So of course, in the previous slide I said the closeness can be defined in various ways. So this has been studied in like I said, low rank approximations under the Frobenius norm, where the difference matrix is. So this is A is the difference matrix for us, and so the Frobenius norm is what is the parameter that is being optimized. So we want a low rank matrix which is closed in this sense. So this has been studied by Deshpande under the name low rank approximations. So there are basically randomized algorithms which can sample a small portion of the matrix and come up with a matrix which is close to a low rank matrix. So that's basically sampling based approximation algorithms called. But that's all again an approximation to the low rank matrix. And under general matrix norms, I mean we can define matrix norm to be under two different norms, alpha, beta. I mean, this is the general form, nothing better is known. I mean, so it's wide open in that sense. How do we, if we consider different norms and norms? And the related question is again considered by Deshpande. It's under the name subspace approximation, where they say that okay, we want to come up with a low-dimensional linear subspace, such that so we have these points in the space, and we want to come up with a low-dimensional space, such that when projected down to this plane, I mean we want to project down such that the distance. Okay, so we want to represent all these data into this projected into this plane, and under the metric that So the D will be the Euclidean distance to the points in the space H. Okay, so that is the metric that we are going to use, that they use in the subspace approximation. So okay, so I just mentioned the related work, and okay, so let's get to what we are going to talk about. So we are going to talk about the Hamming weight. So we are going to talk about the difference between, okay, so m minus n. Basically, this is what the will be, and so that is studied under the name matrix rigidity. So let me define it. So given a matrix M and a rank R, the rigidity RMR is the number of entries of the matrix that we need to change to bring down the rank below R. Okay, so that is defined for, so we are working over some field, let's say, so we parameterize based on the field 2. Now, why is this interesting? I mean, it's interesting in the complexity theory setting, in two settings. So, one is that it was proved in 1977 that by Valiant that if for some epsilon, so we are talking about a matrix. Let's look at this matrix as a linear transformation, and given X, we want to compute, let's say, Mx. So what is the vector to which this linear transformation comes? So we want to compute Y. Okay. Okay. So what is the complexity of this? I mean, so when we say complexity, we are allowing gates. We are talking about a circuit which computes Y given X, and the circuit can have gates which are the functions inside could be linear gates. Okay, so it can compute linear combinations of the input, basically. So we are working out again over a field. So if what Valiant proved is that if the rigidity of the matrix M is something like superlinear, n to the 1 plus delta, then the linear transformation cannot be computed by linear size logarithmic depth circuits. So that's kind of a lower bound against linear size circuits. Okay, now this is by Valiant, and another work, Rasbarov in '89 proved that if we have a better bound for the rigidity of a family of matrices, which is the, I mean, so this is so n square by 2 power log r to the order 1 is supposed to be better. Okay, so this is asking for a stronger bound in the rigidity. We are all asking for lower bounds in rigidity. I mean, we need to change at least these many entries to bring down the rank below epsilon n in the first case, and in the second case, something above that matter. So what is the consequence? That it has a separation result in the communication complexity setting, but I won't get into the details of this, but maybe we'll look a little bit into the, I mean, not the proof, but what are the implications. So again, like I said, the first result says that if the rigidity of a matrix is lower bounded by a superlinear function, where M is an n by n matrix, it's n to the 1 plus delta, then X to the Mx, that linear transformation cannot be computed by linear size logarithmic type circuits. Okay, now that says that, okay, if you have a lower bound on the matrix rigidity, then you can say that, okay, there is a lower bound on the circuit size. So, but we don't have any matrices of that much rigidity. So the attempts after that were to prove that certain matrices, the explicit family of matrices, have high rigidity. So there were lots of candidate matrices. Okay, so before that, maybe I'll just make a point that rigidity can be easily seen to be, when given any r, it is upper bounded by n minus r whole square, meaning that by changing n minus r whole square entries, you can always bring down the rank below r. And this is the number of entries that you need to change at least, because by each change you can hope to bring down the rank by at most 1. So rank 1 minus r is the lower bound, obvious lower bound. So what you are looking for is where exactly is this value in between. So the conjecture is that, not the conjecture, what we want is that we want something like that, n to the 1 plus delta for a rank, the r, for a value of r which is epsilon n. Okay. Now the attempts were based on Vandermonde. So I'm sorry again if I missed some credits in this, but yeah. Okay. So Vandermonde matrices were attempted by Rasbarov, Pudlak, Sharplinski, and Locum in I mean the lower bound is n square by r, which again does not fit in our context because when r is epsilon n, this loses one m. So all these were all the first three attempts were on these Hadamard matrices and parity check matrices of linear codes. So all were attempted to prove lower bounds which are superlinear. But finally, it's in a recent paper, Locum proved that if your matrix is allowed to contain square roots of prime numbers, so the matrix will be over complex, the rigidity can be proved to have a lower bound of n square. So that n square will actually come like n into n minus 16r. I mean, what do I put it in square? So it's omega n square. So then finally what we have is now is a lower bound on one explicit family, but it's over complex numbers. Okay, but arbitrary finite fields and over rationals is wide open. I mean, nothing like that is known. Okay, so that is about lower bounds. Now let me get back to computing rigidity. So we want to compute the rigidity, and this has, I mean, let me motivate this in a vague sense, but I mean, of course it's not exactly correct to say that this is a motivation, but I just wanted to mention roughly the connection. That I mean, in the Rasborough-Rudich setting, what they argue is that there is a concept of natural proofs in which all the lower bound proofs that are currently known fits in. So what they define is, I mean, if you remember Rasborough's talk, there were three conditions, which were, one was usefulness, and the second was okay. So let me read it down. So useful, effective, effectively computable, and dense. Okay, so variance reduction, variance proof could actually be thought of as a property, that is the high rigidity property, being identified as a property which is useful. And it can be argued, I mean, I won't go into the proof, that among the n by n matrices, the density of highly rigid matrices is high. So we have the third condition too. Now, I can say that we are looking for the second condition. I mean, we want to say that how effective is, or given a matrix, how efficiently can you test whether the matrix has high rigidity. So that the question that we will be considering will be of the similar flavor. But this is not exactly true, because there are two big holes, like the question that I was asking Rasborough that day. So there are two requirements, because the Rasborough-Rudich setting is over Boolean circuits. So the notion of natural proofs we need in arithmetic circuits. Even that is not clear whether it exists, because the notion of pseudo-random generator, they are not naturally extended to arithmetic circuits clearly. So then one needs to fill in that gap before I can argue like this. But I just wanted to mention the connection that modulo these two, there is a rough motivation and the setting. Then another thing is that we are proving lower bounds against linear size circuits, whereas natural proofs are working against larger parameters like polynomial size. They don't care about, I mean, they don't care about whether we introduce another linear factor in the proof. So natural proofs does not really fit in that sense. Okay, so there are modulo these two. There is a motivation for looking for the effectiveness of this rigidity as a combinatorial property. So basically, what we want to do is that we want to analyze the complexity of given a matrix. Can I compute the rigidity of the matrix? Okay, so that. Okay, so there are many complexity classes in this slide, but I'm not going to go into the details. But I just mentioned the main things that I wanted to say. So the interesting part is that the problem that we are looking at is rigid MRK will be the problem given a matrix M, a values R and K is we want to test if R and R is less than or equal to K. Okay, so that is the problem that we want to solve. Now the result is that over a finite field, let's say that this F is finite, one can see that it's an NP. So the algorithm will say that given a matrix M, you want to R and K, you want to test if changing K entries suffices to bring down the rank below R. What will you do? You will actually guess, the NP machine will actually guess the K entries that I need to change. And then, so since you're working over a finite field, you can actually guess the entry to which it needs to be changed. So then the NP algorithm follows from these two facts, but it crucially uses the fact that we are working over a finite field. Now, if we are not working over a finite field, we don't know any computational results about this problem. I mean, that is wide open, so we don't know anything. But if we are working over F2, the GF2 basically, so then the bound is exactly NP complete. So there is so that is also proved by reduction by this Pandey. We'll get into the reduction just to be for the completeness. So the interesting part is that, I mean, in this setting we have something which is, when we look for effectiveness, we got NP completeness. So okay, so that motivates whether we can fill up the two gaps in the Rasborough-Rudich sense that we have. Okay, so that is, and other cases, I mean, so these are all classes sitting inside P. So basically, in all these cases, when the K is a part of the input and K is a constant, we analyze various settings. And for each of them, so of course, if K is a constant, then there are only polynomial mini matrices that you want to test. Like, if the number of entries that you're allowed to change is a constant, let's say 5, and if I choose the various 5 entries that I need to change, there are only polynomial mini matrices that I will get. And I want to test if at least one of these polynomial mini matrices have rank at less than R, which means that there is a possible. Okay, so I'll get into that. But the main point is that all of these are inside P, the other restrictions, and all these classes are classes which sit inside P. But rather than defining them, what I will do is I will simply say that for constant K and for 0-1 matrices, digit K reduces to singular. I mean, singular is where you want to test whether a matrix, given matrix is singular. Okay, so it's sufficient for constant K, it's sufficient to test whether the matrix is singular. And that's quite an easy proof. It follows the same thing that I just said.
So what is a singular matrix?
No. What is the program?
Okay.
To make.
Yeah.
To make a matrix with zero determinant.
Right. Exactly. So that is a singular problem. Singular matrices are matrices which have the determinant 0. Basically, rank is n minus 1. Right? At least, I mean, at most n minus 1. Right. So yeah. So we will just reduce this, give this reduction. The reduction is quite easy. So if K is a constant, we need to test if there is a set of at most K entries of M, which when flipped yield the rank, matrix rank below R. Okay, so the number of such sets is bounded by S equal to 0 to K and choose S. Okay, in fact, n square chooses. Okay. Right, so that's a polynomial, and we'll try all of this explicitly. So it's basically a explicit search will work. That is the argument. So M1 to MT are matrices. So you want to test if MR is in digit K where K is a constant. Basically, it will be, this will be if and only if there exists a matrix in this list which is having a rank at most R. Okay. And using standard techniques, I'll just say, so that also I need to invoke some results of calendar wheels and basically to convert this to singular. And yeah, so the second part of the reduction will be basically from there itself. Okay, so that kind of roughly gives the reduction from rigid to singular. In fact, the other way is also true. So rigid Mn 0, where K is 0, it basically tests whether the matrix is singular, because you want to get to below rank n without changing any entry. That is possible only if your matrix itself is singular. So that directly gives the hardness for this. And for arbitrary K, what you can do is you can make copies of this matrix. So let's say I make some copies, and basically you can amplify the gap between the yes instance and the no instance. So if M is singular, then we know that at least one dependent row is there in each column, in each row, in each of the blocks. That will give us the result that it's contained in yeah, so if M is singular, then we know that at least one of them is, and that will give us the result that rigid n, the rank, okay, so we'll make copies of this matrix, and the rank of this matrix n will be n times the number of copies. So the number of copies is k plus 1. Okay, so basically we tensor it with ik plus 1. Okay. Now if to make this matrix n singular, if m is already singular, then the big matrix n is also singular. But if m is not singular, then to bring down the rank below this value n times k plus 1 minus k, we have to change at least k entries, because by changing one entry you can hope to bring down the rank by at most 1. Okay, so that is so that is roughly the proof. Now let me just quickly give the reduction NP hardness proof over GF2. So that is again due to this funding. So the reduction is from nearest code word problem. So we fix a linear code which maps m bits to n bits over F2, and the generator matrix, let's say, is m by n, and we are given a received vector and a distance k. We want to check if there is a code word from this received vector which is nearer to the received vector. So okay, so we want to check if there is a code word x such that delta xy is at most k. So delta xy is the Hamming distance. Okay, so that's the nearest code word problem. Now to give the reduction, what from given this instance, what we'll do is we'll make k plus 1 copies of the matrix G. So since the picture is not clear, so there are 2 plus 1 copies, and then that vector y will be put on top. Okay. Now what we want to claim is, so this is a matrix M that I found. Rm okay. So to begin with, since we are working on a code, so we can assume that m is less than n. So we will try to map m bits to n bits. So G is a full row rank. Basically, they found the basis of the code space. So G is of rank n. And here, if we make copies of G, so the rank of this matrix is either m or m plus 1, depending on whether y is a linear span of disk. So now, okay, so let's say that we want to prove this claim. So we are asking about rigidity of m with respect to rank m minus 1, meaning that how many entries do I need to change in this matrix to bring it down to the rank, sorry, we should say m. So to bring its rank down to m. Now if y is already in the code space, we know that the rank is n. Okay. Now if y is not, then okay, so y is in the span of, let me do it, row span of m. Then we know that y is a code. Okay. So then this is trivially true. So if there's nothing to change, then we have the. So suppose that y is not in the span. Okay. So y is not in the span, and we are asking, can I change at most k entries such that to bring down the rank below. So if I try to change k entries, since there are k plus 1 copies of G, I will have to, if I start on changing G, I will have to leave at least one copy of G untouched. So that will say that I don't get any incentive in changing, because y is anyway in this row span of, y I have to make anyway y in the row span. So what that means that we can say that the number of the entries that you need to change will have to be in the vector 1. Okay, not that, yeah, so we don't get any incentive on changing this G, because you can't change all the G's anyway. You are allowed only k changes, and there are k plus 1 copies. Okay, so then, yeah, now let's say that we could, so the optimum change will be clearly y to Z where Z is a code word. If Z is a code word, then it's in the span of these. It's in the span of these rows of this generator matrix, and yeah, that naturally defines the closed matrix with rank n. Okay. Now that's the reduction. And the one thing to note is that the parameter exactly gets preserved, and that says that yeah. So if it's k, the distance, I mean the reduction is approximation preserving 2. So we get some approximately results for rigidity, which is basically from the approximability of nearest code word problem. So what we know is the constant factor in approximability. There is a constant alpha such that it is NP hard to distinguish between Rm r minus 1 being less than k or greater than alpha k. Okay. And something stronger is known, assuming that NP is not contained in big time into the log n. So it's a standard inapproximability result where yeah, this is a constant factor in approximability and this is a factor which is more than a constant. Okay. So that's about inapproximability. Now, yeah, okay. Now, so we talked about so all this inapproximability works over F2, and like I said, over rationals and over infinite field we don't know anything. So we looked at another problem, and there is a related problem, which is the min rank problem. So let F be a field, and E and S be subsets of F. So min rank problem is equipped with a matrix whose entries come from. Oh, sorry about the notation. So this E and this E are supposed to be the same. Yeah. So all these E's are supposed to be the same. So F is a field and E and S are subsets of F. So the matrix entries come from E basically, and there are some variables x1 to xk. So x1 to xk are indeterminates whose value we want to find. Okay. So let's define the ES min rank of M over the field F, which is the minimum rank possible for when I substitute this x1 to xk with some values in S. What is the minimum rank of this matrix that you can achieve in the field F? So it's a very general setting where you are given a matrix over E and you want to change assign values to these variables from the solution set S such that the rank of the matrix is minimized over the field F. So this is the min rank problem. This has been studied by Buss, Hansen and Sally. I think 1993. Not sure. Okay, so that's a min rank problem. And what do they have? And their results are basically this, that I mean, if the rank is computed over Q and the entries of M come from Q, but the solution set you give only integers. Basically x1 to xk can take only integral values. Then you can show that the problem is undecidable. And over F2, if all these, so basically E equal to S equal to F equal to F2, then it's NP complete. Oh, sorry about the third row, it should be F, not F2. So for over an arbitrary finite field, what we know is just membership in NP. Interestingly, there is a result upper bound P space when solution set is allowed over reals and rank is computed over reals. But notice that the input is over rational, so the representation is not a problem. So okay, so this I'll just give 2 seconds to digest this slide maybe. Yeah, so we have an undecidability result in the basically it's result Buss, Franks and Shank, and yeah. So when entries of M are from rationals and the computation and solution are over reals, then it's NP hard but in P space. Okay, so this is about min rank. Now what is the connection? Min rank is the version of min rank where I allow every variable only exactly once. So the x1 to xk, although they can appear in the matrix, but they cannot appear arbitrarily, like one variable can appear only once. Now how is this reduction? We will just guess the entries. So how is rigid as an NP to one min rank? given the matrix, we will guess the k entries that we want to change and put them as variables. So we will put them as variables which are different, like x1 by xk will be different. Yeah. So and then ask what is the one min rank that you can achieve, and that will give you the rigidity equation basically. So rigid is naturally in P to one min rank. Right. So guess the entries of the matrix to be changed and replace them with distinct variables. But the bad news is that we don't know about one min rank problem, much about one min rank problem either. So I mean, basically this did not give us much, but that's just something which we can use if something better is known for one min rank. Okay, so that is where things are for rigidity. Okay, so let me, so that's about the general rigidity question. Now let me switch to another version of rigidity, which is called bounded rigidity. So what you say is that in the general version that I defined, for the matrix M, you only counted the number of changes that you make. You did not count by how much can I change an entry. So bounded rigidity also says that I won't allow you to change the entries arbitrarily. You can change them by at most b. Then how many entries do you need to change? Okay. So the bounded rigidity question is the number of entries of the matrix that we need to change to bring down the rank below R. If the change allowed per entry is at most b. So we don't. Okay. So that
can we say that we change one entry a few times, each time by b, but to accumulate the change?
No. So basically, if n is the target matrix and m is the starting matrix, what we are counting is m minus n, the bound on each entry of m minus n.
So bounded rigidity may be just defined for some matrix.
Sorry, I didn't.
So for some matrix, bounded rigidity may be just defined, or infinite. Or
Exactly. So yeah, so we'll come to that. That's right. So they need not exist for all matrices. So we'll actually say something like that. Okay, so the bounded rigidity question is given M, B, R and K. So B is the bound, R is the target rank and K is the number of changes that are allowed. So R and BR is it less than or equal to K? This is the question that we want to answer. Now there is another formulation which is natural in the setting, that for each entry in the matrix you define an interval defined by the bound Mij minus B and Mij plus B. So the question will be, is there a rank R matrix in the interval defined by this square bracket A, by which I mean the interval defined by this, such that M minus B has at most non-zero, K non-zero entries. So this is another formulation. Now we have more tools to use using that. But before that, let me come back to the question that he was asking, why should there be? I mean, why should it be defined at all? Okay. So let's consider this matrix with some huge values of 2 power k on the diagonal. So okay, I'll use this result which is easy to prove. I'll leave the. So if a matrix is for all j equal to I, this is less than ai. So basically what we say is that the diagonal entry on each row is dominant on the sum of the other rows. Then I mean, if this is a strict inequality, then it's easy to argue that n is full rank or non-single. I mean, this follows from various
modules should be on there.
Sorry?
Modules.
Yes, that's right. Thanks. That's right. Yeah, so this is what we'll use in this context. I mean, so I won't get, so it's actually a 3-line proof. But, okay, so this is the method that we start with. And yeah, like you said, it need not exist. So it's defined, undefined for values 2 power k, which I mean, if we don't allow these entries to be changed by at least these many entries, the RM and the rigidity question that we are asking for will be undefined. Because basically you cannot kill this diagonal dominance without changing those entries by at least that much. Okay. Now, yeah. So now the natural question is, it may be undefined in some cases. So for a given a matrix bound D and target rank R, can we efficiently test whether R and BR is defined? Okay. So this is basically equivalent to the question that I said in the previous case. Is there a rank R matrix B? So the existence is the question in that interval. Okay. Okay. Now the bad news is that that is also NP hard. In fact, a restricted version could be shown as NP complete. So what we want to test is that, let's say that we are testing whether the rank is n or n minus 1. So not for arbitrary rank. We're basically testing is there a singular matrix in the interval. Now there are many tools in the literature of linear interval equations which one can use here. So okay. So then yeah. So let me show that this problem is NP complete. So we'll show the membership. So like we said, if for the bounded version of rigidity, the naturally defines an interval for each entry of the matrix. And then we are asking for, is there a singular matrix in the interval defined by this bounds on each entry. So we basically have, so let me look at M as a n by n matrix as an n square dimensional array. A matrix, if the matrix has variables in it, it will be multilinear polynomial in those variables. And this is a crucial fact which we will use. And now then the result is that okay. So the result is more general than the determinant now. Now it's for any multilinear polynomial px1 to xt. Consider the hypercube defined by the interval on each xi. So let's say that we have an interval assigned for each variable. And let's consider the hypercube defined by interval of each xi. So there is in this axis there is a variable and there is an interval defined for it. And in this axis there is one. So this naturally defines a hypercube. Okay. Now what we want to prove is that okay. So the claim is that if there is a zero of the polynomial inside this hypercube, then there is a zero of the polynomial on an edge of the hypercube. So what do I mean by an edge? You fix all variables except one to the extreme values. So there is an interval for each variable. So you fix value of every variable to except one to the extreme values. That will give me an edge of this hypercube. Now the claim is that if there is a zero inside this hypercube, then there is a zero on the edge. Now how does this help us in the NP upper bound? Because this is a matrix which can be represented easily. I mean, if the value of these variables are yeah, so that we call zero on the edge lemma. Now we use that. It gives the upper bound. So okay. So the problem that we are looking at is RMB n minus 1. We want to test whether there is a singular matrix in the interval. Now what we will guess is that so there are some variables in the matrix after the so yeah. So given the matrix M, we'll guess the values that we need to change. So that will give us some hypercube like this, and we can actually guess the edge where the zero is sitting, if at all a zero exists. So the NP machine, it will be able to find the zero if there is a zero. Okay. So then how will we verify this? That this is actually a zero? We'll just make sure that the signs of this determinant polynomial on these sides are different. Why is that so? Okay. Now let me give some more idea about it. Okay. So I'll just mention the proof of the zero on the ends, and that will make the algorithm also clear. So that is the diagram there. So okay, so now what do we have? So let me prove it in 2 dimensions instead of 3. Let me prove it in 2 dimensions. That is a picture. So suppose that I have a zero inside this square. Okay. So the polynomial that we are looking at is on two variables, x1 and x2. Now, if this line is corresponding to one linear setting of this polynomial, so if there is a 0 in this, then the signs of the polynomial, the value of the polynomial at these 2 points should be different. And so on a walk from here to here, you should change the sign somewhere. And that will give a 0 for me on the edge of this hypercube. Okay. So basically, you can say that between this and this, so it will be an inductive argument. So so this is, let's say this is positive and this is negative. So polynomial takes value positive here and negative here. They should take opposite values because it is 0 here. Now if this is plus, let's say that this is also plus, and let's say that this is also negative, so then there should be a 0 here. But if all the other cases can be easily verified. So if this is negative, then this 0 will be shifting to here, since these are opposite signs here. Basically we are using the fact that restricted to one variable, it's linear. That's it. So that is a 0 on the edge lemma. I mean, this implicitly appears in the work of Holjak and Rome. We think this proof is much simpler than this. Okay, now what is the NP algorithm? The NP algorithm will, like I said, just guess the edge on which the 0 appears. And basically verifying that will be easy, since if there is a 0 on the edge, the signs of the opposite ones should be. Okay. So that is the okay, so that is the membership. Okay, so NP completeness actually follows from Holjak and Rome, where the reduce an interval is singular if and only if, so they have this parameter theta j. The j is the orderless matrix. So they have a singular matrix in the interval if and only if we can actually argue that if and only if Rm and theta is different. So basically the reduction that they have will give us a NP hardness for the boundary rigidity too. So the reduction is from max cut problem, and so they showed that checking interval singularity is NP hard. That gives us the hardness too. Now I'll look at the other version of this problem, which is the max rank problem. Basically, we want to, so till now we talked about reducing the rank. And that was also motivated by some of the practical applications and Walian's lower bound. But suppose that for the fun of it, we turn around the problem and ask, what is the minimum number of entries that you need to change to raise the rank or increase the rank above some given value? Now that is naturally connected to the max rank problem, which is a complementary version of the min rank problem that we talked about. So there the problem was given a matrix M with entries from, I'm not stating it as general as the min rank problem, but so with entries from F and K variables. The max rank problem is the maximum rank that you can achieve by substituting these variables from the underlying field. So that's the max rank question. And something different is known for max rank. So these two problems behave very differently. So over integers, over integers there is a randomized polynomial time algorithm which can test if max rank is less than k. Okay, and this problem is again studied by Bus, Hansel, and Sallet, and they give this randomized algorithm. But I won't get into that. But over GF2, the problem is NP complete. So this gives a variety of problems by varying the underlying field. Now again, max version of rigid. Max version of rigid, which I just explained. So given a value R, you want to test if changing k entries suffices to increase the rank above given value. It's in NP to 1 max rank, where 1 max rank is the special case like we had in the min rank. where it appears exactly once. Okay, so that is the one. Now here there is some good news that max rank is NP. So that's a nice result by Guillem and again by Grota. Right. So the independent results. So max rank is in P. Now the interesting part is this puts max version of rigid in NP2. Okay, so remember that in the original rigidity version we just had NP to 1 min rank and we didn't know anything better. Yeah, so that is the situation with max version of rigidity. I think I'll conclude with some open problems that arise in this. So a better upper bound for computing rigidity over Q, rational. But so the problem is that we don't know anything better than recursively enumerable. We don't know any algorithm at all over Q. In the sense that why did our NP algorithm fail in the case of Q? We could guess the entries that we need to change, but we don't know to what value we need to change those entries. There's no bound on the amount of change that you may need to bring down the rank. So that is left as an open problem. And another thing is if we specialize this to when the rank is a constant, when the target rank that we need to get is a constant, let's say 1, and we want to say, so the problem will be given M and K, we want to check if changing K entries reduce the rank below 1. R is not even a part of the input. Even then we don't know anything about it. We believe that the problem is still NP hard. Another thing is that remember that in this argument, so the bounded rigidity upper bound, we had a 0 on the edge lemma. So where we said if there is a 0 inside the hypercube, there will be a 0 on the edge of the hypercube. For this argument, we specifically use the fact that we are looking at determinant polynomial. One determinant, we want to make it 0. So if there is a 0 inside, there is a 0 on the edge. That's what we basically used. Now, if we want to generalize this for arbitrary rank matrix, so a rank below R will say that all the R plus 1 by R plus 1 subdeterminants, something which is above R plus 1 by R plus 1 size, will have to be zeroed out by the changes that we make. So that will say that we basically want an intersection of the zeros of some polynomial some many polynomials. We are looking for a common zero of many polynomials. So basically what we are looking for is if there is a common zero of a set of polynomials inside the hypercube, can we argue that there is a common zero on the edge of the hypercube too? Okay. So so this was for one polynomial because the setting was only for singular, non-singular rank. Okay. So I guess I'll leave it. So those are the three main questions that came out of this. I think I'll stop. Thanks.
Is there any questions?
Let me ask some stupid question probably. Well, as far as I know, we know that most functions require big circuits.
Okay.
Also, you said that almost all matrices are rigid, but we cannot find an explicit function that requires a large circuit, and we cannot find a matrix that. Well, but William says that if we know some matrix with nice amount of rigidity, then we can construct a circuit. So is the reverse statement true? Or, I mean, if I give you a function with an explicit proof on...
You mean the converse of the theorem. So that is not known. So basically you're asking that if a linear transformation is computable by a log-depth linear size circuits, can you say that the rigidity is low?
Yeah, for example.
Right, that's not known.
Okay. So let's thank you again. We have 2 minutes break before our last. I
give you a basic notion of average case complexity, and in the third part, join those two notions, and I show how to construct one-way function based on average case hardness assumptions.
So it's one semester course or 2 semesters?
Half an hour course. Okay. Intuition of one-way function is very simple. Function f is one way if it's very easy to compute, but very hard to invert. Example of a well-known example of candidate of one-way function is the descriptive logarithm. F of x is just x to the d modular pq, then p and q are big prime numbers, but if we don't know p and q, it's hard to invert this function.
So if you think that it is function of x, then this is a RSA function.
Yes.
And it's not the
discrete
discrete logarithm is a function of d.
But RSA is also an example of one-way function.
But in one half, our course is the same. RSA and discrete logarithm, more or less okay. Yeah.
Some cryptographic motivation. The main motivation is private key crypto systems, or everybody uses it when authentication. For example, when you check your email by a password. Server saves only the result of application one-way function of the password, and if somebody has rights to read the app of password, he cannot authorize because he should invert it. The system just compute f of input or f on the input and compare it says. Okay. Other application uses not just one-way function. Public key systems we need one-way function with trapdoors. For example, a RSA function. If we know p and q, it's easy to invert. But if we don't know p and q, it's hard to invert, and p and q is a trapdoor. And digital signature requires one-way permutation. Permutation that is length preserving and biaxial. Okay, let us define worst case one-way function. It's a very simple definition. Function f is worst case one way if it's computable in polynomial time, and its inverse is not computable in polynomial time. But we need a second assumption, third assumption that f is honest. That is, the length of input is bounded by polynomial of output. Otherwise, it's not interesting. Very simple function, maybe one way. The main effect of this definition that it's maybe that only one input is hard, and on other input there is a polynomial algorithm that's inverted. And it's very easy to see that if p not equals 10p, then there exists worst case one-way function. For example, if p not equals 10p, we cannot solve that in polynomial time. Then we may consider the following function on input phi and sigma. If sigma phi and sigma, if sigma is specifying assignment of formula phi, then it outputs phi. And in other case, any trivial satisfied formula that has satisfying assignment. If we invert such function, we recursive algorithm that solves certain polynomial time. But, as I already said, worst-case M1 function is not very interesting. Cryptographic one-way function, we say that function f is strong one way if f is computable in polynomial time, already f should be honest, and any randomized polynomial time algorithm may invert function f only not more than polynomial fraction of inputs for any polynomial. However, there exists a more weak definition, a weak one-way function. It differs from strong one-way function that this is wrong definition. It explains.
What is wrong here?
Okay. First,
This is why we should have transparencies, so that we could.
okay, first two is the same, and last should be that the probability there exists one polynomial, but only one, and in the previous definition was any polynomial, such that any randomized polytime algorithm inverts function with probability less there will belong, and here should be less than 1 minus 1 over 2 PR10.
So just you don't mean 1 minus. So the probability of that thing should be at least 1 over P of n. Yeah. Yeah.
Okay. However, there exists a well-known theorem that if there exist weak one-way functions, then there exists strong one-way function. Okay. Now I say some words about average case complexity. When we consider worst case complexity, we study problems or languages. And in average case complexity, we study not only problems but the distribution on the problems. Ensemble of distribution is just a sequence of distribution on inputs on the length n. Distribution is just a function such that it is quality code. We consider a function only from bit strings to bit strings. And distributed problem is a pair of the function from bit strings to bit strings. I write this by such a way because I consider also multivariate function. It's reasonable when we invert function, and I mean to compute function is mean that we compute any value. The pair of the function and ensemble of distribution. Okay, let's define what is mean average polynomial time. I think the first idea that the problem is solvable in average polynomial time, that there is algorithm with expectation time polynomial. But this definition is not very good. Let's consider one example. That we have algorithm. It works only on one input time to the n and linear on other inputs. Its expectation is linear because probability 1. And let's consider algorithm with working time square of previous one. and its expectation would be exponential. That's why this definition is not very good. We say that the distribution problem FD can be solved in polynomial average time if there exists algorithm A, which is T of 10 T of x time, such that it computes the value of function x, and there exists epsilon more than 0, such that the expectation where x from the distribution, that t of x is epsilon, is linear.
No, the algorithm is deterministic.
Algorithm is deterministic. Okay, there is an equivalent definition, and it's more convenient. The definition is okay, and we denote as f average p all functions that all distributed problems and can be solved in average polynomial time. The equivalent definition is as follows: the problem FD is solvable in polynomial average time if there exist algorithms A with two parameters, x and delta. The algorithm A is polynomial in size of x and 1 over the delta. And there are two properties. First of all, the algorithm A either computes function f or answer I don't know. But this symbol means I don't know. But the probability that algorithm answer I don't know is less than delta. If I'm not mistaken, the second definition is due to Pagliazzi. Some words why they're equivalent, I show why from second follow the first one. If we have...
I'm sorry, that was after Levin or before in Pagliazzi's definition?
After Levin.
And he has proved that they are equivalent.
No, but yes, I think he more or less said it.
Yeah, really?
The first one is by Levin or?
By Levin.
First is by Levin. That such a strange definition could be only by Levin.
Why they are equivalent?
Because A of x delta, you just use the algorithm A and waiting for 1 over delta or 1 over delta something, depending. So just the delta is used as a time bound, I guess, yeah? We don't need any change of the algorithm to go from 1 to second, yeah?
It's easy to see why why from second definition follows first one.
Yeah, but from the first, if you have second definition, then we apply A to different delta probably.
The delta 1/2
and then until something happens, and then we are happy and so on. No, I think that if it's more difficult to remember the definition than to understand why they're equivalent. So I think we can just let's proceed and return.
Dima, are you cheating? I believe that the original definitions were for languages, and these definitions are for functions. Is it the case, or I missed something? These definitions, are they for functions or for languages?
But is it really important?
They are for functions.
Yes.
Okay, and Levin's definition was for languages.
And functions.
That's all? Okay.
But not for multi-valued functions, right?
Okay, by the similar way we define a notion of randomized average polynomial time and the class f average BPP. The distributed problem FD is random class f average BPP if there exists randomized algorithm A of x and delta, which is also polynomial of size of x and 1 over delta, such two conditions which are similar to previous, by instead of A with delta is either the correct answer or I don't know, we put the probability of otherwise less than 1/4. And a second condition changed by the following. That means that the probability of x correspond to distribution of the probability of answer I don't know. This probability is by randomized bits of algorithm A. But if this probability that will in a probability more than 1/4, or it may be only less than the delta part of x.
No, but it's very strange. It's very strange definition for multivalued functions, because the standard argument with amplification doesn't work here. So the choice of 1/4 looks. Imagine, for example, that the problem is for each x to compute some digit from 1 to 9, except for one forbidden digit, and this forbidden digit is extremely complicated. So we can just produce a random digit between in the range, and according to your definition, we have a good algorithm. But it wouldn't be a reasonable thing, I guess.
Do you suggest a different definition?
Yeah, but not for. I suggest to assume here that the function is single value, and that's okay, right?
Actually, will we actually have functions that are permutations, or at least we can assume it? No, we can't.
Why it's not first condition or second condition?
No. Let me give just an example. Imagine we have a function which multivalued function for each x. It takes values from 0 to 9 except for one value, and this one value is very depends on x in a very complicated way.
So it's a very easy problem.
In your sense, it's an easy problem because you can just randomly generate a bit.
But it is indeed a very easy problem. You can easily solve it in a randomized time, just guess.
No, but you don't want to be labeled as your theory is 1/4 theory, but not 1/10 theory.
Sasha says that
It's dependent on that.
It depends on this 1/4, and there is no reason to believe that 1/4 is the true
The problem is 1/4 easy, but 1/20
difficult.
We will apply it to the inverse of some cryptographic one-way function. And fixing 10 inputs means that we try to encrypt one of 10 variants. Exactly. And this is not the same thing you are interested in.
Well, maybe we can say with definition, just for every x, we should take a fixed element from f of x and set it some y, and say that the probability of a of x delta is y, or I don't know, is more than.
Well, I think that we don't need to change the definition. It is a reasonable definition.
Yeah.
If a adversary needs to guess just one preimage of our hash, he doesn't care if there are some complicated cases, if he can always give us the one.
I agree with Misha. This is a reasonable definition, but do not apply it to your stupid function, Sasha.
But you want to say that for each specific constant we have a separate definition, and then we have to carry this constant everywhere with your.
No, for large classes of functions, say for single-valued functions or for inverse of polynomial computable function, this is a sound definition, and it is in the sense that 1/4 is not important. Replace it by any epsilon,
And
and
in any case
it will not change.
Cryptographically reasonable definition, but it is indeed not robust in the sense of BPP. You can't amplify.
Yeah.
We will say that our adversary must not have such a tool. And in this sense, we do agree to call some rather problematic case allowed to adversary.
So you claim what you claim. So you can choose one of two options. First, you claim that 1/4 is a very important constant and we'll insist on it. And second, claim that for each constant you have a separate theory, but all the theories are rather similar, so we do not worry about the specific value.
In cryptography,
Let me satisfy your work.
for large numbers, cryptography is always
Sasha, I think I have a proposal to satisfy everybody. Let's change the definition like that. Say that this guy belongs to that class if there is epsilon less than 1/2, so that this is true for when we substitute epsilon for 1/4. Right?
Exists. There exists somewhere.
There exists epsilon, say, less than 1/2. Okay? Do you agree? Okay. Is my definition reasonable?
No, because we cannot assume, estimate the consequences. Let's go, but
okay.
But something is.
So Sasha is satisfied now.
No.
Proceed.
No, there's definitely some misunderstanding here, but let's proceed.
Okay.
Anyway.
The class distributed FP is the class of languages from MP with languages of function with polynomial samplable distribution. That is, the distribution can be generated by polynomial time computable function from uniform. And we define average case reduction. The distributed problem FD is reducible to distributed problem F prime D prime if there exists two polynomial time computable function G and H such that the first condition is very standard. If we want to compute function f of x, we first of all compute h of x, and after it we compute the function f prime, y is one of the results, and after it we apply function g.
No, this is also strange because definitely your definition should be the problem becomes weaker if you increase the image of f. Yeah. If you increase the image of f, if you allow more values for given x, your problem becomes weaker. So the reduction should be monotone. If you get a better f prime with smaller set of values, and if it's reduced to weaker f prime, it should reduce to smaller f prime, and so you cannot have this in both direction equivalence, I think.
I didn't understand.
So imagine.
What condition do you?
Imagine the second one. Imagine that f prime is just d prime is the same as d, but f prime is just a smaller set for each x. F prime is a smaller set than f.
That is, for example, f is multivalued and f prime
is
just one value of.
Yeah.
Okay.
So definitely f is easier than f prime. So probably you would want to have the reduction.
F is easier than f prime, and what?
So probably you will want to have the reduction of f to f prime. In a reasonable definition.
F to f prime? No, of course.
If f prime is more hard, so f is reducible to f prime. Solving f prime, we can solve f.
Yes.
Yeah.
So f reduces to f prime.
Yeah, but here is not. It's not the case for this definition.
Why it is not the case?
It's the case.
Why it is not the case?
If the more values, it's more.
Because there is an equivalence in the second condition.
So yeah,
There is function
here is not.
a function G.
No, of course, the reduction should be trivial. You cannot use any reduction except for a trivial function. So the equivalence in the second condition just should not be there. I don't know what should be, but it's not the.
Okay,
But let's continue. Okay.
in addition to have left arrow, but if we consider such definition, all works.
Okay.
Yes, it's not standard.
Там же вообще правильная сторона написана. Здесь правильная сторона написана.
This I don't know. It's too difficult for me to say. I don't know. But, the equivalence should not be put. Thank you.
And the second condition is that the distribution should not change more than a polynomial. And there is two lemma. First problem, fd is reducible to f prime d prime, and f prime d prime is an f average p, and the second one, and similar to the f average bpp. Let us prove, for example, the first lemma, and maybe help to understand the second condition.
No, maybe if we have a maybe we should go further and see what, because if the condition is right and we understand this, we were understanding also the lemma. We would understand also the proof of the lemma. It should not be just nothing. You do not do anything non-trivial with the lemma. Yeah. So maybe we should skip this and look what happens further.
Okay.
Yeah. Yeah. That's really interesting. What you dream about. Yeah.
We don't know nothing about the existence of cryptographic one-way functions, and we don't know any reasonable complexity assumption. For example, it's very good to have some statement like p not equals to np, then there exists a cryptographic one-way function. But there are no idea how to prove it. But maybe it's more simple to prove something like this, that distant p, if distant p not in f average p, then there is one-way function. But this condition is still open question.
And the word cryptographic should be in the second line as well.
Yeah, but please say again what is the dist np is what?
Dist np is
What was in the first slide?
np with this
np with
sample distribution.
Ah, it was not in the first one. Sorry.
Yeah, and so this, not every problem in NP with a sample distribution can be solved
fast from the average by a randomized algorithm.
Yeah, but for example, if there are cryptographic we know that if there exists a cryptographic one-way function, then P is not equal to NP. So do we have the implication in the second line? So if one-way function exists, can we be sure that this is not in here? Or not?
Something like this.
At least we have something very close, because, well, we have to fine-tune our definitions, but something very close indeed is not trivial, but is known, was known.
But now is not, yeah. Yeah, okay.
The inverse direction
Yeah.
was known.
Okay. Suppose that we have function f that is polynomial time computable, but inverse f with distribution as a result of function f of uniform distribution is not computable by randomized average time polynomial algorithm. The question is it possible to use f to construct cryptographic one-way function? The answer is yes, it's possible, and is our main result. The all known facts just very similar to inverse statement that if all functions from P with uniform distribution are in average BPP, then there is no one-way function. It's well-known fact.
Are you sure? Because I know the result, but the same result, but were not f average BPP, but just average BPP.
For languages, is average BPP for function is f average BPP.
Dima claims that it works for functions as well.
Yeah, but since we anyway cannot remember all the classes, can you just explain what you do with the function f? Imagine we have a function which is polynomial time computable, and this inversion is not. So how you get one-way function? What do you do with that? Just how you construct it.
Okay.
Yes, we do.
No, only 3 slides, 2 slides. Okay, we prove the following theorem. If there exists a length preserving polynomial time computable function that inverted cannot be solved by randomized average polynomial time, then there exists strong one-way function. The plan of the proof is as follows. First of all, we define a padding version of function f. We have length reserved function f. Some way we define that input strings is split into 2 parts: the main part and padding. How I say later. X is the main part, Z is a padding. And the new function fp apply function f to the x, and it's change padding to the padding of the same length, but only with ones. It's not hard to see that this new old problem is reducible to a new problem.
Just repeat again. So we have a function which preserves the length.
Yes.
Yeah. Now you add some long, probably string z.
Yes.
And what you do with this pair? Just say it again because it's late and we just
we apply function f to the first part. And the second part we change the padding we change to the string of the same length but only from ones.
And you say that this function is weak
One-way
function. But the length of z depends only on the length of x, or also
no. Z may be any string.
Yeah, but usually when we speak about weak one-way function in standard definition, we have some parameters. So for example, for given n, we consider all strings of length n or some polynomial of n, and we say when computing the inversion, we deal with these strings. How you define one-way function? Probably.
It seems like you would like to define a family of one-way functions.
No, it's just
here f is one-way function that is defined on all strings. One function defined on all strings. Of course, you can split it into several functions, into countably many functions, and make a family, but it just will be not so natural.
no, but the definition, the existence is the same. what means by one-way function? When you say that something decreases, that some fraction of inversion decreases, is it has bound by some polynomial?
Yes.
You know, usually you say the polynomial of n and the fraction among of length.
Okay, here is the length of the total length of the input.
Yeah. So what you still, so the definition is the same. Just so you can consider the restriction of fp to strings of given length. Yeah.
Of course, but it will be a restriction of x and z simultaneous.
Yeah.
X plus z.
Yeah, and then you count the probability of inversion for all strings, all pairs x z of given total length. Yeah,
Yes.
that's what you do.
Yes.
So actually, what you do with f, you somehow mix different lengths of f. Yeah, this is
yes.
what's the main what is happening.
Yes. Yes, and okay.
You have to be reasonable not to ask any questions and make the speaker to speak, for example, for 5 minutes. Do it better, because the speaker is just.
Does he have this?
Okay, let's give him 5 minutes. And this is
Try to foresee what he will speak, but he's the.
Okay, it's not hard to see that the old problem is reducible to new problem. The only problem to show this is padding. How we can understand that the input is all ended and the padding is started. And I say about it later. Okay, if we prove that, the plan, the proof is the following. Let's prove that fp is weak one way. Suppose that there exists algorithm b such that it inverts function fp with a probability more than 1 to the n, 1 over the n. Let us show that fp with distribution fp of uniform is in f average BPP. How we will do it? We'll increase length on the input by to show that to show this we have to construct algorithm A of x and delta. We increase x by to the 1 over the delta. And the algorithm A of x and delta is defined by the algorithm B with long string. By the reason, it's obvious how to define it. The key observation that we define function fp so that the probability of f without p of y and t1s is the same as the probability of just f of y, and it equals to 2 to the minus of f of length of f of y. That is the probability in long inputs of this is the same as the probability of x in short inputs. And after it, it's informal. The probability that B makes mistakes is less than from this inequality is less than this, and this is less than this. And such a way we show that function, that this problem is indeed in F average BPP. And since old problem is reducible to new problem, we conclude that old problem is in F average BPP, but we assume otherwise. And one, is there a question to?
No, that's still 5 minutes.
Don't ask it.
Yeah. No,
please proceed.
I have a question, but not to you. But first, not to you, and second, only after 5 minutes. So proceed.
And in this proof, there one technical problem that not putting, but
It should be changed to Putin.
padding should be economic without it is too expensive to have a single column. Because if we code X column Z, we string X should not contain this simple column. When we reduce one problem to other, there may be exponential increase of probability, and so we should be padding in more economic way. I think it's not interesting how.
Yeah, we can believe it. It's possible.
It is all what I want to say about the proof. And the open question, is it possible to use distant p-complete problems to construct one-way function? If it's so good that from one distant p-complete problem construct a length-preserving function f such that the computer answer is distant p-complete, if distant p is not in f average p, it follows that this function will be one way. But there is a problem that distributions of distant p-complete problems of known is not very good.
Вы можете вернуть теорему, если она была сформулирована? Just one remark about the open question to make it clear to everyone, because it's an important open question. Here is a theorem which looks very much like the answer to this open question. What is the difference? The difference is that if you would like to have this average base hard or something function f, if you would like to have it distant p-complete, to insert a distant p-complete problem here, you will need to prove for a distant p-complete problem, you will need to prove some additional conditions. Of course, we know distant p-complete problems, but they will not easily fit this theory. It is not clear how to satisfy the premise of this theory, though we would naturally assume that distant p-complete problems are the hardest problems in distant p, but and here we of course assume that inverting f is hard, but one hardness does not easily fit another kind of hardness.
Okay. Any other questions or remarks? Sasha, you had a question.
I had a question. Did you understand anything during the 5 minutes and can explain what was said?
I'm not sure, but I should say that the same was for the previous 20 minutes.
So why bother? Yeah, okay. No, cryptography is a very delicate thing, and it should be very really deeply embedded in this thing to understand anything. And very shy. Each year he gave a course on cryptography. It's always very
Which
delicate.
didn't understood.
I went there several times trying to understand what is happening, but it's not that easy. So we cannot hope to understand so fast. Yeah, but
Okay.
okay.
So the event is over. If everybody likes it, we could organize another one in some years.
Yeah, so first, but are there some organizational problems, some papers not filled, something, somebody doesn't know how to do something?